Hello, Professor Todd Elliott. Today is Saturday, the 3rd of May, 2025, and this is a introduction and overview video for optocouplers. If I get some time, I'll make some more, but right now, this is what I have. What is it? Okay, so optocouplers are optoelectronic devices, meaning the input side is a photodiode that's called the emitter, and the output side is a phototransistor, usually a BJT, and it's called the detector because it detects the emitter light from the by the emitter. Okay. Whoops. Sorry about that. I hit the laser pointer and not the pen tool. Sorry. Okay. So this bit here is the photodiode. Now these comes in one little integrated package, and so it's all internal, and so the light then falls upon the emitted light falls upon the exposed base of the transistor, which turns it on. So it's activated by light and not electricity. But anyway, the optocoupler is commonly used to provide electrical isolation between separate circuits having different voltage levels. So for example, if you have a PLC and you want to bring inputs or outputs into it to avoid any possible damage, you can go through an optocoupler. So the two sides are electrically isolated. That isolation voltage is typically well north of 1,000 volts, and so there's no direct connection between the emitter and detector sides. So it's very very safe. Okay, this is an LED falling on a photodiode. Trouble is you can't get there's no current gain. This is much better because you still have the current gain. It doesn't work quite the same way as with a regular BJT, but there's quite an amplification of the current. Okay, so again, the emitter side is the LED, and then the detector side is the phototransistor, and there's no connection between the two halves. 4N26 is it's a very old common optocoupler. There's many different part numbers with different characteristics available. This is from the data sheet. So it's a little 6-pin package, looks like a logic chip but half the size. And you can see the transistor comes out on pins. 5 is the collector, 4 is the emitter, 1 and 2 is the emitter diode. Just if you might find it interesting, is that the forward voltage here to turn that on, it's somewhere around 1.2 volts based on my tests. Okay, different packaging styles. Almost gone. Okay. Okay, this is the data sheet. Here's just some interesting specifications. Maximum forward current for the emitter, that's the LED. Okay. Up to 100 milliamps. Now, you see, I don't know why they have two versions, but they do. So the M suffix, it's a white color package. The black one is no M. That's just the ones that I have. Okay, and they have different current ratings. Okay. The collector to emitter breakdown voltage, VCE, in both cases is 30 volts. That's fairly typical range for a transistor. I said a bit ago that the nominal, my test, the turn on voltage on the LED is about 1.2, 1.25. They're giving you this range here. Okay, so it's more than a standard diode, but less than an LED. Okay. Isolation voltage, okay, depending on the package style, but 5300, 7500 volts. Okay, so they're good where there's shock hazards or a fault, lightning strike or something. Well, maybe not lightning strike, but that's kind of unpredictable. But any ground faults or anything, power surges, it's not going to let that through. Okay. So these are just some of the specifications, and you don't have to spend any time looking at them unless you really want to. I do have some nice circuits, which I created, which if I get some time I'll do some videos on them. You might find them I found them interesting building them. But one of the key parameters for an optocoupler is called the CTR. It's called the current transfer ratio. On the x-axis, we have the forward current, IF. That's the LED current. And this is the CTR on the vertical axis. So this graph shows that when the forward current is at 10 milliamps, this is red line I added, the CTR is 1. So that means then that this is the curve. You can see then the ratio. It's not a 1-to-1 like with the BJT. We have the DC current gain. If we're up in the active area, this is less true when it's saturated. But when in the active area, if we increase the base current, we increase the collector current by the same amount. So it's a linear relationship. This is clearly non-linear. Okay. All right. Just test circuit. The most optocouplers that I've worked with, you have to add pull-up resistor from the collector to VCC or pull down emitter to ground because it's not included in the package. So you do have to add that in. And again, I have a really nice little circuit showing both of those in one application that if I get around to doing I will eventually. I just don't, too many things on the go right now. Okay, and this is just a little test circuit, but here's how it works. Your input data switch, if you make it 5 volts, R1, the 100 ohm resistor limits the current. Light shines from the emitter, the emitter onto the base of the detector, and then this transistor turns on the LED. Okay, so providing 5 volts to the input turns on the optocoupler, and then that's uses the LED. And you can see here, this is like the collector resistor. So just think of it mostly as a normal BJT switch. Okay, that's just the current relationships. Okay, it just talks about if you adjust this here, it's being used as a rheostat. As a potentiometer. It's varying the input voltage, and you can control the current through the input diode. Okay. And you can just simply see then that as you increase the input current, you increase the output current. So notice, remember we talked about the CTR ratio. Notice how it's not linear at all. Okay, it gets more so up here, but it's not linear at all. So because it's not a normal transistor, but that's okay. It doesn't need to be. Okay, so these are some real test results from another circuit, the one I was talking to you about, and I'll get around to doing a video on that sometime. But these are just some of the test results that I have from that, where I'm plotting the emitter current versus the detector current. You can see it's not linear at all. Okay. Emitter current versus transistor detector voltage VCE. Look, as you keep increasing the current, then as the transistor saturates, then the collector emitter voltage falls down. So this is in cutoff. This is essentially saturation. Okay. And this is the detector voltage VCE on the transistor versus CTR. Okay, and as you can see then, right, from this point here to here, like about here, it's a very abrupt change. But once you're up in here, it's kind of linear. Anyway, we'll talk about this on another video. But I had them, so I just quickly threw them in here. But anyway, have a good one. Thank you.